Given a single paned glass window that is 2 centimeters thick and having the shape of a perfect square with 50 centimeters length on each side, what is the resistance to heat flow for this window given that the glass has a thermal conductivity of 0.96 watts per meter Kelvin? And what is the rate of heat flow if the outside temperature is 4 degrees Celsius and the inside temperature is 21 degrees Celsius? Now, the equation we were presented with on the key concepts page was a heat, let me make that a little bit better of a cue there, a heat per time interval, which is really the rate of heating. So when we're talking about rate of heat flow, that's what that really represents, was equal to the thermal conductivity times area divided by, we just said divided by D, which ordinarily we might say is distance, but in this case that's actually the thickness of the glass. I mean, the picture I drew on the key concepts slide was of a rod, but it turns out you can kind of think of a glass window as being sort of like a really thick and very short rod separating two regions of air at different temperatures, and then that was multiplied by delta T. So that was the formula that we had there. This can actually be restated, this formula, as the change in temperature is equal to the thermal resistance to heat flow multiplied by the rate of heat flow as expressed by a Q over a delta T. And that works as long as this thermal resistance to heat flow has the expression of D divided by K A. So the first thing that we're asked for in this question is actually to find that, which given the numbers that are here, the 2 centimeters thick can be turned into a 0.02 meters thickness. The K value, which was the thermal conductivity, is 0.96 watts per meter Kelvin, if I can squeeze all that in there and still leave enough space. For the area, since it's a perfect square with 50 centimeter length sides, I'm going to look at that as 0.5 meters and then square the whole thing, including the unit there. And then if I put those numbers into my calculator, it says 0.08, like 333 repeating. Maybe just 0.083 is good enough for what we're doing here, looks like. And let's look at the units there. It looks like we've got a meters up here, but we also have a meters down there. I think actually, because you could, if you imagine like multiplying by the reciprocal, I think this meter would combine with that one, and all the meters would combine, and then you'd still have this watt per Kelvin down here, but that would turn out to be a Kelvin per watt. And that actually makes sense based on the way we defined what the resistance to heat flow is based on this formula, because to balance this, I'd want to have kelvins on the left side is equal to kelvins per watt times watt, because a joule per time or joule per second really is a watt. So that's the answer I'm going to provide for that part. And then for the second question, where it says what is the rate of heat flow, we're really being asked to calculate Q over delta T, and so that of course should be equal to one way of looking at it is you could just say it's equal to delta T, like since we've already calculated what this resistance to heat flow is, because you could use this formula right here and just plug in Ka over D like we just did, but since we already have this resistance, and if we divide both sides of this formula by this R sub T, which is the thermal resistance to heat flow is what I'm calling it, then that would look like this. And so then I'd have 17 Kelvin is really the delta T going from 4 degrees Celsius to 21 degrees Celsius. And you could say, well, maybe it should be 17 degrees Celsius, but when it comes to a delta T, that's the same thing. And then that would be divided by the 0.083. I actually, in my calculator, didn't round off, and I put in more threes here because it was actually 0.08333 repeating. Oops. Let me make that W look more like a W for the watts there, because this should turn out to be some number in watts. And if you don't round off too much, it winds up being an exact value of 204 watts. So that gives me two answers to check. And there we go, 0.083 Kelvin per watt and 204 watts check out.